can pull that up. So hopefully that's visible, and let's make this. So for this problem, I think most of you were able to figure out the correct shear force and bending moment diagrams. I did see that quite a few of you probably made a calculation error in computing the forces here, which affected your final result. But overall, I don't think it was a. Most of you did well on this. Where in this problem, the only thing that you needed to account for was the bending of this beam. I said that the strings you do not need to account for. The bending moment diagram should have been like this with -12. And if you scale that with p divided by 8, then you would get 3/2 p prime. I also saw that quite a few of you, well, not quite a few, but some of you tried to correlate the displacement at E with displacement at A or D, which is correct for this problem. But that complicates things a little bit because you have to now solve two different problems rather than being able to use the same real and virtual system as this diagram right here. You would have to draw a new bending moment diagram just to find the displacement at D, for example, right? Which is okay if you would still get the same result. Any questions on this problem? Okay. So this problem, the real structure should have been, as I told you, I think even in the hint for homework 5 that I gave you guys, the reaction was just a pure torsional reaction, 4 kip feet here. The shear would have been constant 2 kips throughout. If I'm going to apply a load at D, it would cause negative bending moment through this leg CD. That bending moment would get converted to torsion, and that torsion would then come back as positive bending moment 8 and down back to 0. So I think very few of you got this bending moment diagram correctly, but overall, if you set up the problem correctly, you still probably got most of the points of the problem. But other than that, the virtual system was quite simple. If you apply P prime here, then only this leg comes into, only this leg plays a part, right? Everything else is just zero shear, zero bending moment, zero torsion throughout. So if you take the contributions of this leg for shear and this leg for bending, then you should have gotten something like this, AGA minus 64/3. So this minus is the important thing here, because what it says is the displacement at B would be 64/3 EI, and generally this would be bigger than the shear deformation. So displacement at B would be minus 64/3 EI, which means that since I'm applying P downward here, the actual displacement of the real structure at B would be upward. Okay, which is also something that I tried to explain in the class the other day. All right, any questions on this problem? Okay, and the last one was basically the truss problem solving for the real system and solving for the virtual system. For the virtual system, you should have noted that almost all of the members are zero forces, which also allows you to write, you need to account only for those 3 members which are non-zero force members. You do the real displacements for the actual system, and what you should have gotten was something like this, 607.5 over AE for delta C. The second part, I think some of you did not do correctly. How would this result change if member CF, this diagonal member, if this is too short by 0.5 inch? So if you remember when we did examples similar to this, all we needed to do was to go to CF and add to the real displacement. Okay, we need to add, or in this case subtract, because it is too short, minus 0.5 divided by 12. All that was needed to be changed was uh, this entry, and then 5/5 over 4 times that would be something that gets added to it, and what you would have is this change in the displacement at C. You would get additional horizontal displacement at C if member CF is too short by 0.5 inch. Make sense? Okay. All right. So do please make sure that the totals are correct, and if you find any discrepancies in my grading, let me know immediately. After the class, you can leave your quiz with me. Overall, I feel almost uniformly everybody did better than the quiz, better than quiz one, which, yeah, you will see that when I post the grades, the average should come out to be higher. I haven't checked the average yet, but there were, of course, some people who did not do as well. But yes, yet again, there's quiz 3, quiz 4, final exam, and plenty of homeworks left. So if you have any concerns, come talk to me, and I'm sure you can do better on quiz 3 and 4. I mean, not right now. I think I'll post it immediately after the class. Okay, Daniel. Uh, Answer for what? For this one? Okay. And I'll post this online after the class. Okay. All right. So let's jump back in to what we were talking about last lecture. We were talking about this force method for indeterminate structures. And I told you that for certain structures that we can take advantage of symmetry to reduce the order of redundancy of the system. So if you remember from maybe a few lectures back, when we were talking about redundant systems with a degree of redundancy greater than 1, if you have a degree of redundancy greater than 1, for example, here the degree of redundancy is what? For this problem, the degree of redundancy is what? 2, yeah. If you remove the center 2 supports, it's 2 degrees of indeterminacy, which means that you would need 2 equations of compatibility, which also means that you would need to solve for the flexibilities, at least 3 flexibilities, and at least 2 displacements, real displacements, right? That's 4 or 5 sub-problems at least, right? So that can be a lot of work. And if you can reduce the number of redundancies using some properties of symmetry, that will simplify your job quite a bit. So for example, if you had 3 redundancies, this would be a 3 cross 3 system where you would need to solve 3 plus 2 plus 1, 6, and 3 here, 9 sub-problems. So yes, that would become very cumbersome by hand, and we'll get into the computer methods for that shortly. But overall, the idea is that we would take advantage of symmetry to try to simplify the problem, reduce the number of indeterminacy, and then just be able to solve a much smaller problem. So I was telling you last time, for example, this guy, also 2 degrees of indeterminacy. Here, degree of indeterminacy is 1. If you solve this problem, it is the same as solving half of this problem. You reflect that solution to the other side, and you'll have the solution to the original problem, right? And similarly, this guy, the first example here was a symmetric problem. The second example here is an anti-symmetric problem. It's anti-symmetric because the structure itself is symmetric, but the loading is anti-symmetric. The structure and the boundary conditions are symmetric, loading is anti-symmetric. Even for anti-symmetric structures, you can take advantage of anti-symmetry and solve a slightly different problem, which again, what is the degree of redundancy here? So redundancy is 1, and redundancy here is 2. Redundancy here is 2. Redundancy here is 1. And of course, solving a system with redundancy 1 is easier than solving a system with redundancy 2, as I just showed. Um, how about this guy? We have a structure that's symmetric. Boundary conditions are symmetric. Loading is what? Symmetric or anti-symmetric or nothing? Anti-symmetric, right? Loading is anti-symmetric in this case. So maybe take 30 seconds, see if you can draw the deflected shape of this problem, and then I'll draw it with you. Draw the deflected shape and try to see if you can come up with a half problem to solve this. All right, so let's see what. Before we get into the deflected shape, let me ask you this: what's the degree of indeterminacy or redundancy for this problem? Y2. We have two fixed ends, right? So it's almost like a fixed beam, which is degree of redundancy is 3, right? Even though the horizontal reactions, vertical reactions, and moments at the two ends, those would be three unknown reactions. You are going to get exactly 3 equations of equilibrium. Degree of redundancy is 3. Now the deflected shape is what is going to help us to try to figure out what would be this half symmetric problem that we should solve, because degree of redundancy 3 again means you would need 3 compatibility equations, lots of sub problems to solve. So if we can reduce the degree of redundancy, that would be a good way to go. This vertical leg, the first vertical leg, would kind of behave like a cantilever beam with a uniformly distributed load, and this angle is going to is maintained as 90 degrees, and the same thing for the other leg. Does that make sense? Why do you think we need this here? Why do you think we need a point of inflection here? Right, Mubin? Go ahead.
Yes, the two angles are sort of asphyxity at change from 90 degrees, and the other is association.
Okay, yeah. So if you look at this angle, this is indeed 90 degrees, and this is indeed 90 degrees. I'll mark them as such, 90 degrees. And then if you look at this, it's a negative curvature, and this is also a negative curvature, right? With a negative curvature here, it would go up someplace there. With a negative curvature here, it would go down somewhere here. You would need to have to come back up, and then do that. Which means that if I look at the symmetric half right here, if I look at this symmetric half, then that would be the smaller half problem that I would need to solve in this case, which we can draw as simply as the loading remains like this, what would be the boundary condition here? What would be the boundary condition at this point? Say it again. Pin. If it's a pin, then we are not going to be able to move horizontally, right? So it should be a roller. It should be a horizontal roller so that this can deflect, and maybe I'll draw the deflected shape also. Um, so this guy would deflect kind of like this. Um, it would deflect kind of like that, right? So now here's a question: what's the degree of indeterminacy for this problem? 1, right? It's fixed right here and just 1 extra support here. So degree of redundancy went down from 3 to 1. That would be a much easier problem to solve, right? All right, so there's another benefit of having symmetric structures with symmetric boundary conditions. This problem right here is clearly a symmetric structure with a symmetric boundary condition. But what about the load? Is that load symmetric or anti-symmetric or neither? Neither, right? It's clearly not symmetric or anti-symmetric. But the good thing is, no matter what type of load you have, you can always break it up into a symmetric and an anti-symmetric loading. Okay, so let me repeat that. No matter what kind of load you have on the original structure, as long as the structure is symmetric and the boundary conditions are symmetric, you give me any loading out here, we can always break it up into symmetric and anti-symmetric loading. So if I were to solve this problem, I would break it up into 2 parts. And if I sum up these two, you should be able to see that 4 and 4 we get 8. This 1 and this 1 add up to 2, and this 1 and minus 1 cancel off. We get this original structure that we wanted to solve. Now, in order to solve this system, we have a degree of redundancy 1, which similarly for this guy also degree of redundancy is 1. And if we were to draw the deflected shapes, something like that. And something like that. So, any idea what this vertical reaction would be here? What would be this vertical reaction? Should be 0. So, in fact, if you make use of this symmetry, your anti-symmetric structures sometimes turn out to be determinate. Okay. All right. So, what I would ask you to do now is an in-class exercise where on the next page you you would draw what half problem you need to solve for both of these systems, and without doing any calculations or anything, just set up the compatibility equations, and then we'll move on to the next topic. Say again? No, I'm sorry, I don't have a handout for this. But you can draw it. And feel free to discuss with your fellow students. Rick, go ahead. You can do it both ways. You can solve the original problem, for this original problem, degree of redundancy is 1, or you can look at half the problem, which would still be degree of redundancy 1. So in this case, even though this structure would be difficult, well, not difficult, but a little bit cumbersome to solve if you had chosen this as the intermediate reaction. Breaking it up into symmetric and anti-symmetric will simplify your job. So maybe what we'll do is we'll go ahead and do this together, um, and then at the end of the class you can turn it in. So hopefully you all saw that you would solve either this system or the entire thing as a whole with the center point, with the center support as the redundant force. Similarly, for the anti-symmetric system, you would once again solve this half. So let me solve this symmetric half first. The system that I would solve is this, and I'll draw the boundary conditions in a minute. That's 1 kilonewton per meter, and there's a additional point load of 4 kilonewtons. Now, what should be the redundant structure? What should be the redundant force or moment that I should choose for this half? What should be the boundary conditions, first of all? It would be fixed here, right? And it would be simply supported here, right? So if I draw the deflected shape, that would look like, oops, I think we did draw the deflected shape on the previous page, so that would be something like that. And if you look at half of this problem, that's like a fixed support here with a simply supported end at the other end. So we have something like this, and I would break this up into an underlying determinate system. So this would be equal to a simply supported beam with the same loading plus same simply supported beam with a redundant moment at this point. So for both of these loadings, I can easily calculate the rotation at this end, either going through the tables in the book or just calculating rotations, whichever way you want to, whichever method you want to use. For this one, I can also calculate the flexibilities at this end. So in this case, I would get some rotation theta A, and in the other case also I would get some rotation theta A prime, which would be equal to F, well actually I should use alpha for rotation and moments. The flexibility symbol that we were using was alpha, and looks like I might need to rename this point A. Let me call this A, B, and C, and this is A and B, so this is theta B and theta B prime, which is alpha B B times the unknown moment at that point. So if that's the case, what would be the compatibility equation? What would be the compatibility equation for this symmetric problem? April? Say that again? Okay. What would be the compatibility equation? Anybody else? Hongzi? Theta B equal to theta prime B, which essentially you're saying theta B minus theta prime B, right? Would it be minus or plus? And how do we decide that? Right, so they are in the same direction. That means that the total rotation has to be 0 for both of them. If I add them, the total rotation has to be 0. On the other hand, if I had applied a moment in the other direction, maybe I'll do that. So I'll write compatibility for this case is simply that theta B plus alpha BB and M equal to 0. On the other hand, if I had done let's go back. So if I had applied a redundant moment in the opposite direction, in this direction, let me call that M2, then I would get a deflected shape, something like this, and in which case I would get theta b prime 2, in which case the compatibility equation would be theta b plus, minus, minus theta prime b2, which is equal to theta b prime, or theta b, and let me write this also, alpha b b and 2. Would alpha bb change? No, it's the same location, same moment, just applied in the opposite direction. So the rotation, the sign of the rotation will be taken care of by m2, right? So what we would get here is minus alpha b b m2 equal to 0. Make sense? So the point here is that it does not matter which way you choose your redundant moment. You just have to be consistent with your compatibility equation. If you have the real rotation and the redundant rotation in the same direction, then you need to add them to make sure that the total rotation is 0. If your real rotation and redundant rotation are in the opposite directions, then they need to be equal, or minus has to be equal to 0. So that's the symmetric half of the problem. Let's take a look at the anti-symmetric half. And for the anti-symmetric half, the problem that we would be solving is a simply supported beam, and maybe I'll draw the deflected shape first. So, oops. Something like that. And to solve this system, I can solve this problem. And is this problem determinate or indeterminate? It's a determinate problem, right? So that's another benefit of making use of symmetry and anti-symmetry. Yes, for the symmetric half, the degree of redundancy does not change. R is equal to 1 here, R is equal to 1 here, but R is equal to 0 here. So if you were to try to solve the original problem without taking benefit of symmetry, it might be a slightly longer procedure. But if you take advantage of symmetry, you can solve two simple sub-problems fairly quickly, one of them being determinate, and you can get the solution much faster. Okay. Any questions on the topic of symmetry and anti-symmetry before we jump into a different topic? Miles?
Once you solve for those reactions in the anti-symmetric system, what do you do with those?
In this case, you are solving for, if you solve the anti-symmetric problem also, or if you actually reflect on the other side, you'll see that this reaction and the other reaction will cancel off, and what you will get would be the reactions here. Here vertical reaction would be 0. Here you'll get some reaction. Add those two reactions up here and you'll have the solution to the original problem. Okay. All right, so let's switch gears now and let's talk a little bit about how to solve systems or structures using some very basic computer-based methods. Hopefully, by doing homework 5 and homework 6, you've already seen that solving indeterminate systems can get very cumbersome very quickly. Even with 2 degrees of indeterminacy, it becomes a lots of sub problems of solving you which you do not want to do by hand, right? Which means that we do need to take advantage of the computer tools that we have, um, to be able to solve these real life structures. And as you can imagine, when you go out there to work, maybe in a year or two, people are not solving these indeterminate structures by hand. They are making use of complicated structural analysis programs. Some of them, most of them, are based on finite element methods, which we will not get to exactly, but a very related method, the stiffness method, is what we'll talk about in a couple of weeks. But right now, what I want to make sure is that we can understand some very basic computer analysis programs. So let me ask you this first. How many of you have not had any experience with some computer programming? Very few. And in particular on Matlab. Okay, so, but I assume most of you have some sort of a programmable calculator? No? For those of you who do have programmable calculators, believe me, MATLAB is just like an additional, more advanced programmable calculator, at least the way that we'll use it for now. There's of course a lot more to MATLAB than just a calculator in your hand. Being able to program a calculator on this, or in this case, a computer to solve complicated problems for us without having to go through all these calculations by hand is what we are going to try to learn. Okay. So as we go through this exercise, a couple of things I want you to keep in mind. For no matter what engineering problem you're solving, most of the methods that we use to solve problems boil down the problem to solving a system of equations, right? If you can, if no matter how complicated your problem is, if you can boil it down to solving some system of equations like ax is equal to b, then the computers can chug through that very quickly and solve that. But the way to approach structural analysis problems is what we are going to do is to try to formulate an algorithm to solve a certain structure. So I'll give you an example of the method of joints for trusses. Right? How do we solve method of joints for trusses? By hand, first of all. How would you solve, or given a determinate truss, if I asked you to solve the determinate truss using method of joints, how would you go about doing it? Drew?
You find the reactions and then you systematically go each joint and solve for numbers there.
Right. Right. So you basically find the reactions, and you can actually skip the external reactions also. You can directly go and draw the free body diagram of each one of those joints. If there are 10 joints in your truss, you draw 10 free body diagrams. You get 2 equations of equilibrium from each one of those joints. You set up all of those 10 times 20 equations. You have 20 unknowns, and you solve it, which would be very cumbersome by hand, but you can, that's the purpose of being able to write a computer program to do that for us. And I'm going to talk a little bit about that computer program also. I'll post it on the web. So the idea is that we need to first of all come up with the algorithm. The algorithm is exactly what you just mentioned. Draw the free body diagram of all the joints, write the equilibrium equations for each one of those joints, and get a 20 cross 20 system of equations that you solve. So that's this first step in solving a structural analysis problem. The second important ingredient to be able to write a computer program is to somehow come up with a scheme to store information about a particular structure in the computer. In this case, for example, I'll show you examples of input files for a different truss. For different truss problems, you would have different input files. Your algorithm would work on one input file, give you the solution for that truss. Your same algorithm would work on a different input file, give you a different result for a different structure. You do not want to write different programs to solve different truss structures, right? Every time that we come up with a new structure, we don't write a new code to solve it. We just tell the computer what this new structure is, and this is an important point that I'm sure you'll see in a little later. Quite a lot of times, I see students trying to modify the code or hard code a particular structure in their algorithm. So we have to keep these two things separate. The algorithm is separate, and the particular problem that you're solving is separate. Okay, so if you have one problem today, another problem tomorrow, another problem day after, you can use the same algorithm, same code to solve three different problems. And of course, once you are able to solve it, display and output results. So here's a very quick um, introduction to Matlab if you have not seen this before. Um, and there's lots of other tutorials freely available on the web. Make sure if you are not familiar with Matlab, then I'd encourage you to actually uh, go to the web, look for some simple tutorials on Matlab. So the idea behind Matlab, maybe I won't give you a full demo today, but a few things, if you are able to understand with Matlab, you can actually understand most any programming language then. There are one is the use of computers memory in Matlab. So in any programming language, there is you have access to the computer's memory through that programming language. So for example, if I write a command, say a equal to 10, and I enter that, then what I've done is I've stored the value 10 in the variable a, and that shows up here in the computer's memory. Okay, I could similarly say b is equal to 5 and c is equal to a times b. So by doing all of this, I'm creating variables in the computer's memory on which I can do operations, simple arithmetic operations. I can also create matrices in Matlab. Matlab is actually short for matrix laboratories. So if you're going to be working with matrices, Matlab is actually a very convenient tool. And for structural analysis, if you've not already seen that, you have to work with matrices quite a bit. So you would need to Matlab would be a good tool for that. So for example, I'll create this matrix, 3, oh, 4, 5, back, 4, 3, 2, 1. So this is a matrix that I just created where the square brackets here denote the fact that I'm going to define this capital A to be a matrix. And note that there is a different capital A and a small a in the memory. This semicolon denotes the end of a row. So so there are these simple basic commands that you can execute in Matlab, and there are other two of the most important things that for any programming language, two of the most important things are conditional statements and loops. If you understand how these things work, conditional statements and loops, you can understand any programming language. Okay, so I'll talk about this next time, and I'll see you back on Wednesday. Yes, please do turn in your in-class assignment.